So a z-score is just a numerical value. It's a unitless value. It's just a number that tells you the relative position that a data value is above or below the mean. And in this formula here, x is our value. So generally, if we're converting a number to a z-score, we have a certain value that comes from either a population or a sample. And so this first formula, where we have x minus mu divided by sigma, where mu is a population mean and sigma is a population standard deviation. So you were exposed to standard deviation in the previous section. What we had a different notation for mean, and we had a different notation for a mean and a standard deviation. We had x bar because that was for a sample, because we dealt with only sample data, and we had s for also for a sample. So this formula here is if you are comparing an individual value back to a population. There's a similar formula if you're comparing an individual value back to a sample. So it still represents the same thing. It's the number of standard deviations that this value is from a sample average. And so essentially a z-score, regardless of which formula that we're going to use, represents the same information. It's the number, it's the relative position that value is compared to the average. And here in this example, we are going to calculate the z-score for each of these three countries and kind of compare those values together. So we have the average number of vacation days for a selection of various countries has a mean of 29.4 days and a standard deviation of 8.6 days. And we would like to find the z-scores for the average number of vacation days in each of these countries. So for one, this 29.4 days is not based on an entire population, it's based on a sample. So it says if the average number of vacation days for a selection of various countries. So that selection just means we have a sample of data. So in this case, we would utilize the z-score x minus x bar divided by s, because this standard deviation is tied back to the selection of various countries. So both of those represent sample data. So to convert the 26 days that Canada has for vacation, we would utilize this z-score. We would utilize the z-score formula here: 26 minus the average of 29.4 divided by 8.6. And so that will give us a numerical value that will tell us how far away Canada is from the average number of vacation days from the select country. So its z-score is negative 0.4. And I'm going to go over what those values are in just a moment. We do the same thing for Italy. Figure out what the z-score is, 1.47. Do the same thing for the United States. Figure out what the z-score is, negative 1.91. So we can clearly see, based on the number of days, that the United States overall has fewer vacation days than the other two countries, with Italy being the most, and which is reflected in the z-score. But what we're trying to look at, compared to the average number of vacation days for those select countries, where do these countries fall at? And we can see that the United States is negative 1.91 standard deviations below average, and Italy is 1.47 standard deviations above average, and Canada is negative 0.4 standard deviations below average. Or we could just say, instead of saying negative, we would say 0.4 standard deviations below average. So what that tells us, the average number of vacation days has a z-score of 0. The average is always centered at 0, and then we kind of compare the relative position of those numbers. And basically that just tells us more or less what we can see before we convert the numbers. Italy, it has a much higher relative position, and the United States has a much lower relative position when we look at the average number of vacation days. Now, the use of a z-score in later chapters has a lot more applications than just looking at the relative position, but you're exposed to this basic concept here in this unit to prepare you for later units. So for now, I don't want to give too much away, kind of overload you with information, But for now, you just really need to know that the z-score represents the number of standard deviations that a value is above or below the average. So for now, that's what we're going to stick with. I don't want to give out too much information yet. Now we can also take the same concept of z-score and we can use it to help us find a value. So we already know that, well, in this problem, it says a student graduated from a 4-year college with an outstanding loan debt of $9,650. So that's the value, where the average debt is $8,455. Now this is the average debt for the entire college. So we would say that represents a population. This is the average based for the entire college, not just a selection of students. So we would say that's a population value with a standard deviation of 1,865. So again, these two values represent population information. So I would go with the z-score x minus mu divided by sigma. And in reality, it doesn't matter which formula you write down because they're going to give you the same information, but it does help if you start now paying attention to those little minute details of which formula is more appropriate based on the information provided, because that will definitely come in handy later when it does matter which formula to use. And so we know that the value of x is this $9,650. We know the value of mu, which is the average debt from the college, is 8,455, and we know the value of sigma is 1,865. So what we can do, because now we don't want to find a z-score, we're given a z-score and we want to determine what number represents this position. So in the previous problem, this average of 8,455 represents a z-score of 0, right? If I let this number be my x and my mu, 8,455 minus 8,455 divided by this number is going to be 0. So what we would like to determine is how much student loan debt would a student have if their relative position compared to the average was 1.5 standard deviations above average or 1 standard deviation below average. And so we can take this same formula and we can manipulate it and we can solve it for the x value, right? If I were to, everything has been divided by sigma, so if I were to multiply both sides by sigma, that would give me x minus mu equals z times sigma, and then I'd have to use inverse operations to add mu to both sides. And so I would end up with this formula here, and I could use this formula, x equals z times sigma plus mu, to figure out, well, what's the value? Because in reality, that's what we're trying to determine. The student loan debt represents the value that we're looking for in the problem. And so to do that, it's just a process of substitution. So for A, we have a z-score of 1.5. I'm not going to use this value because I want to find a new value. I'm going to use my standard deviation of 1,865, and I'm going to use my average of 8,455, and that's going to give me $11,252.50, and this would represent the student loan debt that a student would have that's 1.5 standard deviations above the average student loan debt. In a similar process, we do the same thing for B to figure out or calculate, well, how much would the student loan debt be for a student who was 1 standard deviation below average. So this would be the amount, $6,590. And then in the example, in the main problem, this would have a z-score somewhere between -1 and 1.5 because, well, we know that it's going to be a positive z-score because its amount is greater than the average. So if I have one number and I subtract from it a smaller number, then the result should be positive. So we can utilize the z-score, which is a measure of position because it tells us a relative location, to help us also figure out a value. So kind of working backwards. Now the last thing that we want to be able to do as we talk about position is determine what an outlier is. And in this problem, it says the number of incidents in which police were needed for a sample of 9 schools in a county are these values in order to determine if any sample values might be an outlier. So when we talk about position, an outlier is just a number that's extremely large or extremely small compared to the rest of the data set. Right, that's what basic definition of an outlier. We think about these numbers represent a sample of police calls or police incidents, and if they were wanting to summarize the data, like we talked about with the measures of center, with mean, median, and mode, an outlier might affect those measures of center. If a number is extremely large, it might make the mean seem higher than it should be. If a number is extremely small, it might make the average seem smaller than it should be. So an outlier will definitely have some effect on the distribution. And there's a way that we can identify outliers, and we can kind of get away with those outliers. And this concept is in the measure of position section, because we look at quartiles to help us identify outliers. And we'll kind of look at what a quartile is. So in order for us to find an outlier, we have to check two things. And this is kind of a formula that we would use. We have Q1, which is the first quartile, or the lower 25%, minus 1.5 times the IQR, which the IQR is the interquartile range. That's the first thing we check. So we look at that, and if this is going to equal a value or a number, and if any of these numbers in the data set happens to be smaller than that number, then we consider that value an outlier. So if let's say this number, if we look at our data set here, the smallest number is 0. So let's say when we calculate this and we get 2 as the answer, since 0 is smaller than 2, then 0 will be an outlier. In a similar process, we look at Q3, which is the third quartile, or it represents the either it's the 75% cutoff mark, or it's a value that anything below it is the bottom 75% and anything above it is the upper 25%. So it's like a percentile or a quartile. Quartile because it represents different quarters. There's a 25% mark, there's a 50% mark, which is the median. We talked about that in measures of center, and there's a 75% mark. So when we find this value, if any of these numbers is larger than that value, then that number is an outlier. So if, let's say we calculate this and it ends up being 40, well, in our data set we have 48. So since 48 would be larger than this number, then that would be an outlier. So this is a process we would use to determine outlier. So the first thing that we have to do is we want to be able to order the data set from the least number to the greatest number. After we order the data set from least to greatest, then we can go through and do some thing position wise, and we can figure out, well, what's the median in the data set. We have to first find the median, because that, if we recall from one of the previous sections, it will separate the data into two equal halves. So if this is my median, then this is the lower half, or the bottom 50%, and then this is the upper half, or the upper 50%. After we're able to do that, we can look for Q1 and Q3. Q1 is described as the median of the lower half. So if I look at the lower half of the data, 0, 3, 6, and 7, not including 8 because that's the median. So out of these four numbers, the median is somewhere in between 3 and 6. So if I do 3 plus 6, 9 divided by 2, 4.5. So this is my median of my lower half. This is the 25%. It takes the bottom half of the data and it separates it into the first 25% and the second 25%. So this is where we talk about quartiles and percentiles. Then we look for well, really that should be Q3. So this should be Q3. And it's the median of the upper half. So once we do the same process, the median of the upper half should be in between these two numbers, because the upper half is 10, 11, 37, and 48. So those four numbers represent the upper 50% of the data after the median, and then the median would be 24. So that number separates the bottom 75%. So everything below 24 would be the bottom 75%, and everything above 24 would be the upper 25%. And then we want to find, so if we look at the formula here, it's Q1 minus 1.5 times the interquartile range, and then Q3 plus 1.5 times the interquartile range. We have Q1, 4.5. We have Q3, 24. We need to find the interquartile range. Inter kind of means in between. Quartiles are the Q1 and the Q3, and we know that a range is like a measure of spread or a difference between values. So the interquartile range is the difference between the third quartile and the fourth quartile. It measures the spread from these two values. It helps us describe how wide or how large the middle 50% is, because from 25% to 75%, that would be the middle 50% of the data. So that's the number that we have to find. So our interquartile range is 19.5. Police incidents. After we have that information, then we can use these values, these three numbers, to substitute into the formula here to figure out, well, what numbers are going to be what we use to check the data set for outliers. And now we can use the outlier formula to help us determine that. So again, this is our formula we're going to use, and we're just going to substitute in the values. So Q1 minus 1.5 times the IQR gives me negative 24.75. And so if any of these numbers are below this, then that number is an outlier. Luckily, there's no number below that. The smallest number is 0, so this is definitely smaller than 0, so that means there's no outlier on the lower half. And then the upper half, we look at 24 plus 1.5 times 19.5. So that's going to give us 53.25. And again, we look at our data set. We determine the largest number is 48. So there really is no number greater than this. So there is no outlier in the upper half. So based on this information, we could safely say there is no outlier, since the data values are between those two numbers. Everything is between those two numbers. So there really isn't an outlier that we have to worry about.